Hello guys, welcome to another lesson. Today we are looking at exact differential equations. In this lesson, we will touch on 1. Total differentials, 2. What an exact differential equation is about, and then lastly, how to verify that a differential equation is exact or not. Let's get started. Total differentials. If u at xy is a function of two variables, meaning if you have a particular function, let's say u, which consists of two different variables x and y, then the total differential of that function is given by du equals partial derivative of the function u with respect to one of the variables, let's say x dx, plus partial derivative of the same function with respect to the other variable y dy. As stated, this means that we will differentiate the function u at xy with respect to x first. So when we differentiate the function u with respect to x, consider the other variables or any other thing in the function as a constant. They act as a constant at that point. Then we add it to the partial derivative of the same function, but here with respect to y. So it means x and any other thing become constant. Let's take some examples. Example says, the first function for you to find the total differential is u at xy equals 3x squared plus 4xy plus 5x plus 6y plus x. So as we stated earlier, we said that the total differential of the function here u equals the partial derivative of u with respect to x dx plus partial derivative of the same u, the same function, with respect to what? Y dy. Now let's find the partial derivative of u with respect to x. In that case, when we differentiate 3x with respect to x, we are getting 6x plus, we differentiate 4xy with respect to x. So as I said, because it's partial derivative, the 4 and then y act as a constant. So the answer we are going to get is 4y. And again, plus differentiate the 5x with respect to x, we get 5. Here, the whole thing acts as a constant. So that will be 0. Then we differentiate x with respect to x, we get what? 1. So that is our partial derivative of u with respect to x. Now let's find the partial derivative of u with respect to y. The same thing all over again. The whole thing is x. So differentiating a constant with respect to y, that will be 0. Then you are differentiating 4xy with respect to y, we are going to get 4x plus this will give us 0 and this will give us 6. This will be 0. Finally, our total derivative of u becomes the u del x is what? The whole of that. So that will be 6x plus 4y, 5 plus 1, that will be 6 plus 6 dx plus 4x plus 6 dy. And that is the solution for the total derivative of u equals this. Let's take another example. Solution. That the total derivative of f equals the partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy. At this particular point, we tend to do it all together. So the f equals, let's find the partial derivative of f with respect to x first. With respect to x, so the whole of this is constant. so that will go to 0. All of this, when you differentiate that, we are going to get 7y plus the whole of this, because it's with respect to x, it's a constant, so it goes to 0. This gives us what? 10. And then this go to 0, and this gives us plus 16x dx plus, now we are differentiating the same function with respect to y. So here with respect to y, this we are going to get 16y plus 7x plus 6 plus 0 plus 1 plus 0 dy. We have to simplify. When we add the 6 and 1, we will get the f is equal to 7y plus 16x plus 10 dx plus 16y plus 7x plus 7 dy. And that's the answer. So our third example says we should find the total derivative of this function h at s equals what we have there. So in this case, we know that our total derivative of h is equal to a partial derivative of h with respect to x dx plus partial derivative of h with respect to y dy. So find the solution. We're going to get the h equals, we first of all need to differentiate the whole function, and differentiating tan of a particular function gives us sec square of that particular function. Differential of the function within it gives us here with respect to x, so we are going to get y plus differential of sec x, and that is sec x tan x, plus differential of xy, and that gives us y plus differential of sine xy, and that gives us the whole thing is cosine of xy, then the differential of this will give us what? Y. So the whole thing x plus, now partial derivative of h with respect to y, and the same thing as this, but here will be what? X sec square xy plus this, it is with respect to y, but here is x, so that goes to 0, and here we are getting x, and at this point we will get the same thing, but here will be x, so we are going to x cosine of xy, and that is dy, and that gives us the solution for the total derivative of the function h at xy equals that. This exacts for exact differential equation, exact differential equation. The differential equation of the form m at xy dx plus n at xy dy equals 0, where m at xy dx plus n at xy dy represents the total differential of a given function in the interval d, where d is a domain. So when you talk of exact differential equation, it is a differential equation where there's a particular function, say m, which involves x and y, attached by the variable dx, plus another function n, which involves x and y, also attached by the variable dy, where the m at xy dx plus n at xy dy represent the total differential of the given function in a particular given domain. So the exact differential equation always takes the form this. Now the next thing that we are looking at is given the differential equation given a differential equation of the form m at xy dx plus n at xy dy equals 0, how we can verify whether that particular differential equation given is indeed exact or not? First, we will let m equals m at xy, then we compute the partial derivative of m with respect to y. So we compute del m del y. Take note, we compute the partial derivative of m with respect to rather y. So here the x are attached to it, but we are going to compute with respect to what? Y. And also we will let n equals n at xy, then we compute the partial derivative of n with respect to what? X. After this is done and we realize that the partial derivative of m with respect to y gives us the same thing as partial derivative of n with respect to x, then we can say that the differential equation is indeed exact. So this is the theorem that engulfs how to find whether a particular differential equation is exact or not. Let's take one or two examples on that. This particular problem says verify the exactness of the following. First one is 2x minus 1 dx plus 3y plus 7 dy equals 0. So as stated, we need to let m equals 2x minus 1. Let's compute that. So we are computing the partial derivative of m with respect to y, and that gives us, this goes to 0, this is 0. Then n equals 3y plus 7. Then we find the partial derivative of n with respect to x, and that gives us also 0. So hence we can conclude that since del m del y equals del n del x, then the differential equation is exact. Our second example also says you should find the exactness of this, whether this is exact or not. Solution: let m equals what we have here, that's tan x sine x sine y. Del m del y will give us, this goes to 0, and this we are going to get this act as constant, so we are going to have this as negative sine x cosine of y. Then n is also this side, cos x cos y. Del n del x is also equal to, in respect to x, so this actually acts as constant, so we are going to differentiate, and this gives us negative sine x cosine of y. And you can see that del m del y is the same as del n del x, hence it is exact. So we try to pause here. Thank you very much for watching. Please subscribe, share to your colleagues to encourage us to bring you more videos, and then comment too. Thank you very much. Bye bye.